Hello everybody, my name is Luboš Řehounek and I would like to thank you for joining me, and I would like to introduce you to the topic of my research, which is threaded and porous dental implants. I am from the Czech Technical University in Prague and I also work at Červenka Consulting. The goal of my research is to design a novel porous implant. That can be done by applicating a porous structure on the surface of the implant. The reason to do this is that 6 to 7% of implants still suffer from septic loss of stability. Conventional implants are far too stiff and their elastic moduli reach to values over 100 gigapascals, whereas bone has a modulus of about 20 gigapascals or even less. Porosity also allows for a greater surface area to interconnect the bone with the implant and also allows the bone trabeculae to grow inside the body of the implant. These implants are usually 3D printed, as conventional machining does not allow for internal porosity. On these two pictures you can see the gyroid structure on the left and examples of 3 implants on the right. The one on the left is a common threaded implant, the one in the middle is a push-in implant, and the one on the right is the one I will be dealing with today. It is an implant with a homogeneous shank but a porous outer gyroid structure. Some other means of creating porosity on the surface can also be applying a surface treatment, which can conventionally be sandblasting, acid etching, laser ablation, anodic oxidation, or plasma spraying. However, 3D printing usually produces surfaces with sufficient roughness to skip surface treatment altogether. 3D printing also has another benefit, which is the ability to create porosity on the inside, which machining cannot. However, some level of machining is still necessary as the implant has to be prepared. For example, you need to machine the internal hexagon or the external hexagon or the internal thread for the screw that connects the abutment to the implant shank. On the figure on the bottom, you can see the popularity of the word gyroid in titles of scientific literature over the years. As you can see, over the past 20 or 25 years, popularity of the word gyroid has been skyrocketing in titles of scientific literature. Before I explored the possibility of gyroid structures, I dedicated myself to exploring the more traditional trabecular structures. Those are also porous structures that have beams, but unfortunately they are very prone to discontinuities, splitting of individual beams, and they also have very bad heat dissipation during printing. As you can see from the images on the left, the trabecular homogeneous junction suffers from discontinuities at the junction. This leads to eventual tearing and complete unusability of the specimens. From the figure on the right, you can see scanning electron microscopy images of said discontinuities and also another defect, which is slack inside the individual cells. To design the gyroid structure, we need to consider the main parameter is pore size. Other important parameters are wall width, the global elastic modulus E, which also corresponds to the overall porosity, the used material of the structure, which influences the mechanical properties, cytotoxicity of the material, and the variant of the structure. There are 2 variants, the tubular and sheet structure. The tubular structure can be seen on the image on the left, while the sheet or wall-like gyroid variant, which I used, is seen on the right image. The optimal pore size from literature is 400 to 600 micrometers, which is not too small to inhibit nutrient and blood distribution, but also not too large to prevent actual beam trabeculae ingrowth. The literature indicates that the shape of the pores doesn't matter. The wall width of the gyroid structure is influenced by the grain size of the powder we are printing from, and its minimum, which is circa 200 micrometers, was basically set by the printer's lower resolution limit. The global modulus E indicates the overall porosity of the structure, and the more material there is, obviously the higher the modulus. Low modulus is desirable and preferable to eliminate the effects of stress shielding, but we cannot go too low with the modulus because there are also requirements on strength. As we can see from the table on the right, most manufacturers still use the trusty Ti6Al4V alloy and also various variants of the commercially pure titanium. I think this is mostly because traditional materials are standardized, whereas beta alloys are not. However, the use of beta alloys could be beneficial as they also further lower the material modulus. Overall, the material must be biocompatible, non-cytotoxic, and obviously the value of its modulus also influences the value of the modulus of the entire structure. The table on the bottom shows material properties of most commonly used dental materials. So 5 grades of titanium, and then for comparison there is a single beta alloy. Notably, the CAD environment cannot be used for modeling the gyroid structure for the purpose of finite element simulations, because the quality of the approximation of geometry and surface tessellation is very bad. As you can see from the images on the left, the ones labeled A and B, those correspond to the CAD generated gyroid structure. As you can see, there is a lot of geometry errors, a lot of disconnecting nodes, and a lot of overlapping faces. This is obviously completely unusable for finite element method, so I chose the instrument MS Lattice, which is a MATLAB developed instrument instead, to generate better quality gyroids, which can be seen on the images labeled C and D. Also, you can see the single gyroid equation with the modified spatial coordinates. It is a triple periodic minimal surface that is combined using the sine and cosine functions. I analyzed a total of 3 implant variants, a gyroid, a homogenized gyroid, and a threaded variant. You can see their geometries here. They use the same outer dimensions, but their material distribution is different. The porosity of the gyroid is 0.7, and the goal of the simulation is to compare the common threaded implant variant to the gyroid implant variant, which is also modeled as a homogenized layer of specific properties from material tests. A brief research of the boundary conditions other authors use indicates that loads are always set as a combination of an axial and an off-axis load to also generate a bending moment. The computational times are very interesting because porous structures are very time-consuming. Therefore, I expect the method of numerical homogenization to provide better and more easily obtainable results in shorter times. I also performed a short mesh sensitivity study. You can see the 5 varying levels of mesh coarseness on the images on the left. The variant with only 1 element per wall width was not even analyzed because the mesh would be too coarse, and I tried to analyze the other variants with 2, 4, 10 and 20 elements per wall width. The results of the mesh sensitivity study can be seen on the graph. In the end, I settled for variant B with only 2 elements per wall width, while still knowing that maybe a little bit more elements would be preferable, circa 3 to 4. However, when analyzing for that many elements, the simulations took dozens or even hundreds of hours, and the computation times increase exponentially, often to levels which are not really feasible and surely not usable by clinicians. I would expect the numerical homogenization method to be a great step up from this method of direct modeling. The properties of individual materials can be seen from this slide. For bone, the density was determined by the individual patient-specific scan, kindly provided by Mr. Hideyuki Mimata, for which he has my thanks. And the gyroid and threaded implants have these following material properties. The homogenized variant has a modulus of 1.2 gigapascals and a very low yield and critical strength, which are derived from mechanical tests on a gyroid structure with the same porosity. The results of the simulations, which can be seen here on buccolingual sections, show that the homogenized and gyroid variants both show decreased peaks of stress, which is beneficial. and also a more even distribution of stress, which is also better. The result we strive for here is a more evenly large loaded area with overall higher values of stress to prevent stress shielding, but without significant peaks of stress. As you can see from the image on the left bottom, the risk factor for the homogenized variant is peaking over 20%. The peaks is at about 50%. So the initial design of the gyroid structure would have to be modified to have slightly larger modulus. As the modulus determines also the overall porosity and therefore strength, I designed the modulus to increase from 1.24 gigapascals to 2.67 gigapascals, which is the value for another specimen that I have the data available for from previous mechanical tests. I reanalyzed, and from the image on the bottom right, you can see that these material properties should be enough. The results on mediodistal sections show that the equivalent stress, which is the images on the right, is just about the same for all three implant variants, with slightly better distributions for the gyroid and homogenized variant over the threaded implant, but the results for risk factor on the mesiodistal section show a far superior stress distribution for the homogenized and gyroid dental implant variants. Also, the values of risk factor in bone peak only at about 30%, so there are no significant peaks of stress. To summarize everything, I think porous structures are not only suited for dental implants exclusively, but are just as good or maybe even better for larger joint replacements where the geometry allows for more space for application. The gyroid structure was found to be a little bit on the weak side, so it was redesigned and reanalyzed to have a modulus of 2.7, which was enough, but overall I think the modulus should be fine if we design for about 3 to 10 gigapascals. Also, porosity can be combined with beta titanium alloys, which allow for even greater reduction of material modulus. To make these analyses more precise, I think it is important to broaden our understanding of contact conditions and make them more realistic. The homogenized and gyroid variants are not entirely in full agreement in the simulations, and I think that accuracy of the simulations could be improved by knowing the level of osseointegration. That can ultimately be determined only from an in vivo animal experiment. I also think that numerical homogenization is preferable, as the computational times are feasible and not as bad as with direct analysis of gyroid structures, which can take hundreds of hours. I would like to thank everybody who made it this far for listening, and goodbye.